All right, good afternoon. Just resuming with functions, and we left off last time with operations between functions. And now, for what we have in the case, page 225, and for numbers 10 through 26 even, okay, now we're looking at an array of functions, whereupon we have for f of x, okay, we have this to be defined by negative 2x, and we have in the mix, okay, we have g of x, okay, and we have g of x is equal to the absolute value of x plus 4, and we have also in the mix, okay, we have the function h of x, which we have to be the reciprocal of the binomial x minus 3. Okay. And looking at what we have for function values, okay, now for number 10, okay, we have, we're trying to find out, okay, just what the value of g minus h of 2 is going to be. And there are at least a couple of ways that you can go about this. And just sort of tying in just the earlier terminology, we have applying the general case. Now, we have, say, if I had g minus h of x, again, you have your difference function, and here we have defined by g of x minus h of x. And for g of x minus h of x, you have g of x. Okay, we have at the absolute value of x plus 4. And we have minus h of x, which we have to be 1 over x minus 3. And if I were to take the general case, all right, from this, okay, so I would have for g minus h of 2, and for what I would have here, so you have the general expression here, and so with x at 2, so I have the absolute value of 2 plus 4 minus 1 over 2 minus 3, and we have 2 plus 4 is 6, and you have minus, okay, and you have 1 over 2 minus 3, so you have minus 1 over negative 1. And for the absolute value of 6, okay, this comes out to positive 6. Subtract negative 1, and this is going to translate out to 6 plus 1. So for the output here, we come out to 7. And also, if I had taken the approach, let's say just going ahead and tackling, this is just another way here, okay, so I have g minus h of 2, and we have g of 2 minus h of 2. And if I were to identify just what g of 2 and h of 2 are right away, okay, so I have with g of 2, again, I have g of x, you have the absolute value of x plus 4. So g of 2 is going to be the absolute value of 2 plus 4, which in this case is going to be the absolute value of 6, which will come out to 6. And as for what we have in the case of h of 2, for h of 2, okay, so you have in accordance with h of x, which we have as 1 over x minus 3, okay, h of 2, we have 1 over 2 minus 3. So 1 over negative 1, so this will go to negative 1. And so we have, in terms of the follow through, so you have g of 2, okay, it's going to be at 6. And we have minus, and h of 2 we have at negative 1. And just in the follow through, okay, so we have what's going to be 6 plus 1 is equal to 7. Okay. Now, for what we have in the case of number 12, and tell you what, I think I'm going to just copy this trio of functions here. Okay, so for what we have in the case of number 12, okay, so this time we're looking at h times g of 4. Okay. And so in the case of number 12, okay, so you have h times g of 4 okay. And again, you can use like the h of x times g of x approach, but again, you could also just go ahead and arrive at the values ahead of time. So this would translate to h of 4 times g of 4, and just looking at what we have for h of 4. So h of 4, again, you have in compliance with h of x, so with x at 4, so you have 1 over 4 minus 3, and 1 over 1 reduces to 1. And for what we have in the case of g of 4, g of 4, you had the absolute value of 4 plus 4, and so we had the absolute value of 8, and that goes to 8. Okay, and so we have for the result here, okay, so you have h of 4, okay, so that is going to be 1, and you have times g of 4, so g of 4 we have at 8, and 1 times 8 is equal to 8. And again, you can take more than one approach, but if you just go, since we're looking at just h times g of 4 and no other inputs, we just, you can just go ahead with the specific case, which I did. Now, and what we have now with regard to number 14, and we have, again, so just referencing the very same functions. Now we have here, okay, we're looking at f plus h of 5. Okay, so in the expansion, okay, now you're looking at f of 5 plus h of 5. And so just looking at itemized in case we need f of 5 and h of 5. So again, f of 5 you attain plugging in 5 for x, referencing f of x. So f of 5 is going to be negative 2 times 5. So we're going to have it negative 10. And for what we have for h of 5, you have your h of x. And we have h of 5. This will be 1 over 5 minus 3. And so that's going to be 1/2. Okay. So we have for f of 5, okay, we have negative 10. And for h of 5, we have 1/2. And it looks like we're going to have a non-integer result. So you have like negative 10 will be like negative 20 halves plus 1/2. So the result here, you can say either negative 9.5 or negative 19 halves. All right. Now, for what we have in the case of number 16, okay, and we have for this one, okay, we're now looking at h over f of 7. Okay, and in expanding, so we're going to have h of 7 divided by f of 7. And again, so for h of 7, okay, so h of 7, okay, so you have 1 over 7 minus 3. So this will be at 1/4. And for f of 7, okay, f of 7, we were looking at negative 2 times 7. And negative 2 times 7, okay, so this will come out to negative 14. Okay, so just looking at what we have with the inputs. Okay, so we've got, again, so for h of 7, we have 1/4. And we have all over f of 7. Okay, so we have at negative 14. And here we have a little bit of a complex fraction, but just kind of show a little bit of the dynamics that would carry out. Okay, so you have 1/4. Okay, so you have top number is a fraction. And if I divide by negative 14, let me just mention, so looking at division by negative 14. And again, if you divide by a number, it'll be the same as multiplying by that number's reciprocal. So in this case, we're looking at 1/4 times negative 1/14. And so for what we're going to have in the case of the output, okay, so you have positive fraction times a negative is going to be a negative. In this case, you have a negative. 1 times 1 is 1. 4 times 14 comes out to 56. So for h over f of 7, okay, we're going to have a small negative fraction, whereupon we have the outcome at negative 156. Okay. All right. Now, for what we have in the next even item, and we have for number 18, okay, this time we have h over g of negative 4. Okay, so you have for h over g of negative 4, just like what we have with h over f of 7, again, we're going to expand. So you have, this time you have, once again, h is at the top, and now we have h of negative 4. And we have all over g of negative 4. And so for what we have with h of negative 4, okay, so you have 1 over negative 4 minus 3. You have like 1 over negative 7, or which we would have in negative 1/7. And in the case of g of negative 4, for g of negative 4, okay, so you have the absolute value in this case. So you have of x plus 4, so you have negative 4 plus 4. And you have the absolute value of 0, which is going to go to 0. And so for what we're going to have in effect, as we feel in, so h of negative 4, okay, you have negative 1/7. And you have divided by g of negative 4, which we have to be 0. And guess what? With what we have positioned, okay, there's no solution in this one. Okay, that one is going to be undefined. Because here we have a 0 denominator. Yeah, so a fraction to be defined, okay, the bottom value cannot be 0. All right, now in reference to now what we have for the next even valued set of items. Now we're going to a different trio of functions. Okay, and this time we're looking at these three functions we have in the form of r of x, p of x, and q of x. And for what we have for this particular set, and crossing over, and there will be a priority that's going to be placed upon not only the determination of the function values in the general case, but also looking at the domain. Okay, so we have for this next group, okay, so you have for r of x, okay, have equal to negative 3x. And we have p of x is equal to x squared plus 3x. And we have with q of x, okay, so you have equal to the square root of 1 minus x. Okay, now since there's going to be sort of a preoccupation with restrictions. Now r of x, you have a linear function, okay, and with negative 3x, okay, so we have again right now if the expression is negative 3x, x can be 0, it can be any negative value as well as any positive value, so r of x alone has no restrictions. And the same thing applies for p of x, because both x squared and 3x, you don't have a fraction or an even root radical. So you have no restrictions. However, in the case of q of x, we have a radical function which we have in the form of a square root. And for what's going to happen here, because we have a square root, 1 minus x cannot be negative. So that means if it's not negative, now it can be 0 and it can be positive, so we can have that 1 minus x is greater than or equal to 0. And isolating this x term. Okay, so if I take 1 away from both sides, okay, now I'm going to have negative x right now is greater than or equal to negative 1. But now upon multiplying or dividing by negative 1, again, you're going to have the direction of the inequality to change. And so for what we're going to have in effect, okay, we're going to have that x is less than or equal to 1. Okay, so that should be negative 1 times negative 1. Yeah, so we have for the defining inequality, okay, we'll have the x is less than or equal to 1. Okay, so we have, again, for r of x, we have no restrictions. P of x, we have no restrictions. Again, because we don't have the appearance of x such that you would have an undefined expression. But for q of x, if we have anything in x outside of being less than or equal to 1, okay, you're going to have q of x to no longer be a real value. Okay, so you have for this restriction, we're going to have the x is less than or equal to 1. And tell you what, just okay, so you're going to have, once again, in the lineup. Okay, so r of x, no restrictions. P of x, no restrictions. Q of x, we have the x is less than or equal to 1. Now, for what we have in the setup, looking at the functional outputs, and we have with p minus r of x, for p minus r of x. Okay, so you have in expanding now p minus r of x, you're going to have p of x minus r of x. And so we have, in effect, okay, so you have p of x, okay, so you have x squared plus 3x. And we have minus r of x, so we have the subtraction of negative 3x. So you have x squared plus 3x plus 3x. And so we have for the final output, okay, we come out to x squared plus 6x. And for what we have in the case of the domain, for the domain of p minus r of x, okay, because neither r of x nor p of x are going to have restrictions, it's going to follow that we're going to have likewise no restrictions on the subtraction function. Okay, so there's not going to be any restrictions on the subtraction function, since again we have no restrictions on either p of x or r of x. So for the domain in this particular case, this will come out to the set of all real numbers. All right. Now, in the case of what we have with number 22. Okay, this time we have r times q of x. Okay, so this will become r of x times q of x. Okay, so for r of x times q of x, okay, so we have r of x, we have at negative 3x. And for q of x, okay, we have the square root of 1 minus x. Okay, and just taking what we have now, so you're combining the restrictions of r of x and q of x. Again, so we have the operation of multiplication. Again, r of x has no restrictions, but q of x, we have the x is less than or equal to 1. And so we have, in effect, for this output, the restriction is that x is less than or equal to 1. And so for the domain of r times q of x, now I'll state again, with the sum, difference, and product functions, their domain will be on the basis of combining restrictions that applied to the individual functions put together. Okay, so in this case, we have everything coming from q of x, x is less than or equal to 1. And so for the domain in this case, we have going from negative infinity, and we have up to and including the value of 1, and the 1 is going to be in the bracket. Right. And we have also in the mix, okay, with the same three functions. Okay, now I'm just kind of compositing together what we have, so I'm just going to copy yet again. All right, and this time, okay, we're looking at Q over R of X. Okay, and let me give you just a little bit of a segue here. Just kind of focusing upon combining restrictions. Okay, so we're looking at Q over R of X. Let me just mention okay, so we have for Q plus R of X. Let me do this. Okay, so if I have Q plus R of X, so I have combining the restrictions. Okay, so you would have that X is less than or equal to 1. And again, you have the domain. It could be like what we have with R times Q of X. And if I have like Q minus R of X, you're going to have the same bit of history to repeat. And once again, just kind of like what we had with 22, you're still looking at same functions operating and combining the restrictions from R and Q of X. Again, we still have that X is less than or equal to 1. So you have, again, the sum difference and product functions will have the exact same domain. So you're looking at those values of X less than or equal to 1. Okay, but now for 24, now we have the function as Q over R of X. And now, anyway, you're still looking at combining restrictions. But again, you could have a different domain. Okay, and so I was going to kind of put a little emphasis on this. Okay, so combining restrictions now, you have R of X with no restrictions, and Q of X. Okay, we have the X is less than or equal to 1. And guess what? We have, I'm just going to place emphasis. Okay, so with the restrictions so far, this comes only from Q of X. So you have that X is less than or equal to 1. Okay, and 24, this one kind of tricky. Now, looking at defining what we're going to have specifically. Now we have with Q over R of X. Okay, so you have Q of X all over R of X. And Q of X, again, we have the square root of 1 minus X. And for R of X, again, R of X, we have negative 3X. Okay. All right, and now this ratio is in simplest form. Okay, now, just looking at what we have now. Okay, so you have Q of X is in the numerator. So for this part, we have the X is less than or equal to 1. Okay, but just to mention, okay, so we have, again, for Q of X over R of X, okay, I had the square root of 1 minus X, and we have all over negative 3X. Now, for the restrictions, for the restrictions. Now for the square root of 1 minus x, again, for this to be defined, x must be less than or equal to 1. But there's a bit of an added twist to this, because now r of x in direct terms does not have a restriction. But with the quotient function, r of x is situated in the denominator. And guess what? We now have that negative 3x cannot be equal to 0. And so from this, okay, if negative 3 times x cannot be 0, but we have that x cannot be equal to 0. Okay. So we have, in effect, we're going to have the restrictions now. For the restrictions on q over r of x, you're looking at x is less than or equal to 1. And also the x cannot be equal to 0. Okay, and looking at the domain of q over r of x, okay, so this is going to have a feel of sort of threading a needle. Yeah, the determination of the domain, okay, that one sort of challenging, okay, because what is happening here is that right now, okay, we have two values of concern. Okay, so you have 0 and we have 1. Okay, now we have x cannot be equal to 0. So just for placeholder purposes and also for visual purposes. Okay, so you're going to have a hole on 0. Now we have x is less than or equal to 1. So 1 is going to be included. And had it not been for the stipulation, the added stipulation that x cannot be 0, I would have a ray going continuously to the left. But for what is going to actually occur, okay, you're just going to have a line segment, okay, that will go from out to the left from 1 to 0. And then once you go past this little blip, that hole in the graph, okay, we're going to pick up with the rest of what was originally x is less than or equal to 1. But now we have 0 is left out. Okay, and again we have just with the lower limits, okay, we have tending to negative infinity. Okay, so for the domain, okay, if I express in terms of an interval, and reading in order from left to right, okay, so you have going from negative infinity approaching but not including 0. So you have parentheses around negative infinity and 0. And then we have bypassing 0, and the second and last subinterval section, you have going past 0, approaching, and with the equal sign included, okay, 1, okay, is part of the domain, and that is going to be in the bracket, okay. And so this would be the domain for q over r of x. And again, just from the initial standpoint, okay, the restriction imposed, okay, so in the introduction we had that q, this came from q of x, stating that, okay, we know so far that any restrictions initiate from r of x and q of x solely from q of x with x is less than or equal to 1. And with r of x being divided, okay, we also had the restriction that x could not be 0, and so we wound up with this particular domain, those values of x less than 0, and then you had those values of x greater than 0, and in turn being less than or equal to 1. All right, and now for what we have in the case of 26, okay, and just taking what we have once again. Okay, so just at face value, again, R of x has no restrictions, P of x has no restrictions. And if you had like R of x or P of x being divided, like if it were at the bottom part of a fraction, okay, that it could not be 0. But just as a standalone function, no restrictions, and Q of x, again, we have that x is less than or equal to 1 in order for that function to be defined. Now, for what we have in the case of 26, now we have, instead of Q over R of x, we now have, flipping it, we have R over Q of x. And I'll state, okay, so between R and Q of x, R, no restrictions, Q of x, we have x is less than or equal to 1. So we have restrictions so far. Stems from Q of x. We have the x is less than or equal to 1. Now, and looking at actually arriving at our expression, now again, the operation would have to be division. So with the quotient function, there could be possibly yet another restriction or fine detail, okay, that's going to be added. Okay, so you have R of x over Q of x. Now R of x, we have negative 3x. And we have with Q of x, we have the square root of 1 minus x. All right, and guess what? Now, we said that the restriction so far was x is less than or equal to 1, and that was because the square root of 1 minus x cannot allow 1 minus x to be negative, thus x is less than or equal to 1. But now with Q of x in the denominator, again, because of the square root, 1 minus x cannot be negative. And also because 1 minus x is now situated in the denominator, it cannot be equal to 0 either. Okay, so for R over Q of x to be defined, that means that 1 minus x must be positive. Okay, so for the defining inequality, okay, we have 1 minus x is greater than 0. And we have taking 1 away from both sides. And we have that negative x is greater than negative 1. And we have just changing the sign value. Again, if you multiply or divide by a negative, once again, you're going to have the direction of the inequality to change over. And so in this case, we're going to have the x is less than 1. So you have it 1. And now we initially had the restriction to be x is less than or equal to 1. But now we have the restriction now to be that after looking a little further, we have the restriction on R over Q of x, again, to be at x is less than 1. So here you have a hole on 1, and you have a ray that's going to go to the left. And we have approaching negative infinity. So for the domain of R over Q of x, okay, so we're going from negative infinity, approaching but not including the value of 1. Okay, so that would be the interval notation solution for R over Q of x. Okay, and again, we have for operations between functions, again, the sum difference and product functions will have the exact same domain, and it'll be from combining any restrictions from the individual functions. And in the case of the quotient function, especially like these last two cases, there is the possibility that there might be added restrictions. Like in 24, you had developed that x could not be 0. And in the case of 26, okay, it turned out that x could no longer include the value of 1, okay, because q of x is in the denominator. Okay. Now, for what we have in the next category of operations, and this will be what will be referred to as the composition of functions. And upon first glance, this will look like multiplication. But it's not multiplying. And for what we have for compositions of functions, now the symbolism that's going to be used for compositions of functions. Okay, again, it'll look almost like multiplication because you'll have a circle separating, but it's not going to be a closed circle like as you normally put as a dot between the characters. You have like this can be left open, so some might call this fog x, and here you have f and g separated by this circle. You have x, and this is going to be read verbatim. F composed with g of x. And if I reverse the order, okay, and let me, before I do this, okay, so you have f composed with g of x. What's going to happen here is that in operational terms, f composed with g of x, what I'm going to do here is that, now we've got two functions that will be intertwined, and one function is going to be dependent upon the other function. And so the function whose variable appears first, that is going to be the output function. And the function whose variable appears afterwards, this is going to be the input function. So f composed with g of x, okay, that is going to be f of g of x. And what is going to be f at the moment? Okay, so f is just going to be the output. And in the case of just reverse sequencing, okay, and some might call this goth x. Okay, and just in the formal reading of this, okay, so we're going to have G composed with f of x. That's how it would be read. Okay, so goth x is G composed with f of x. And just for what you have initially. So G composed with f of x. You have between G and F. Okay, one is going to end up as the input, and the other part, okay, that's going to be the output packaging. Okay, so now we have f of x is the input. And in the case of g of x, g is going to be, or say g of f of x, now g is going to be the output. And just looking at what we have operationally, say if we have specific terms, okay, that will define f of x and g of x, and looking at their compositions. Now let's say that if we have determining so if you were to determine, so you have f composed with g of x, and we have g composed with f of x, and we'll say we have given, we'll start out like in the first case. Okay, we'll say we have f of x is equal to x plus 2. And we'll say that we have for g of x, okay, g of x will have equal to 2x plus 3. Okay, so you have f of x at x plus 2 and g of x equal to 2x plus 3. Now, if I look at f composed with g of x, okay, and then just intertwining, okay, so f composed with g of x, okay, this is going to be f of g of x. Okay, now for what we have here, okay, so I want to specify, okay, so you have f of g of x, and for what we have specifically now for g of x, okay, g of x we have at 2x plus 3, and the ways you can go about this, I've never taken this approach before, so you'll be the first class upon which I have mentioned this. Now if you notice, you have your output function, you have along the lines of f. Now again, you have f of x is equal to x plus 2. But guess what? F of g of x, instead of x, your input is now g of x. So guess what? F of g of x is going to be equal to g of x plus 2. And now for g of x, now g of x is specifically 2x plus 3 plus 2 And so by then you can just go ahead and combine. Now for f composed with g of x, okay, this will come out to 2x plus 5. Now for the reverse order, we have a g composed with f of x. So I now have g of f of x. Okay, so f of x is going to be your input function, and I'm going to follow through in accordance with the pattern laid out by g of x. So guess what? So you have g of the input is equal to 2 times the input plus 3. Now the input here in the composition is going to be f of x. So if I follow suit in the same fashion, g of the input is equal to 2 times the input plus 3. Well, guess what? So I'm going to have 2 times f of x plus 3. So that's going to be 2 times f of x, and then f of x we have at the quantity of x plus 2, followed by the addition of 3. And we have just in the follow through. Okay, so we're going to have 2x, and 4 and 3 will make 7. So you can have the same variables and how the compositions are sequenced. Okay, you're still working with the same functions, f of x and g of x, okay, but in terms of how they are sequenced, f composed with g of x, g composed with f of x, you're not necessarily going to have the exact same output. Because if you notice with f composed with g of x, the output we have at 2x plus 5. But for g composed with f of x, okay, we come out to 2x plus 7. And let's say that if we're looking at compositions, and we'll say that in this one, we'll say that we have f of x is equal to a quadratic function, okay? And we'll just say we have x squared minus 3. And g of x, okay, we have 2x plus 1. Oh, okay, so for f composed with g of x, okay, so again, we have the input function is going to be g of x. So I have f of g of x. And in terms of how I'm going to follow through, okay, again, you're going to use like the outside. Okay, so you have f, function f. So again, f of the input is equal to the square of the input minus 3. And guess what? F of the input is equal to the square of the input minus 3. And I tell you what, I'm just going to work down. Okay, so I'm looking at the square of g of x. Well, what is g of x? G of x is going to be 2x plus 1. And for the square of 2x plus 1, this will be 2x plus 1 times itself. So this will be 4x squared plus 4x plus 1. And then we have followed by the subtraction of 3. And combining the constants. So it's going to turn out that for this composition, where f is composed with g of x, we'll have 4x squared plus 4x minus 2. And just the reverse sequencing, if I have g composed with f of x, Okay, so again I have g of f of x. Again, g is going to be the output, and f of x is going to be the input. And again, the setup is going to be in accordance with g of x. So again, you have g of the input is equal to 2 times the input plus 1. For the composition, g of the input is equal to the input. What is the input? It is going to be f of x. 2 times the input followed by the addition of 1. Now, in the variable expression, okay, what is f of x? F of x is x squared minus 3. So here, 2 times f of x is going to be 2 times all of x squared minus 3, followed by the addition of 1. And we have with distributing, so we're going to have 2x squared minus 6 plus 1. And it's going to turn out that we're going to have a most difference output with g composed with f of x in comparison to f composed with g of x. In fact, the result here is going to be 2x squared minus 5. And now just in what we have regarding compositions, and we'll get into domain in just a moment. Okay, let's say that if we have and just a couple of problems here. We'll say, first of all, okay, we'll say that we have f of x is equal to two x plus 5, and g of x is equal to 3x minus 2. And we'll say that we have in the second case, we'll say that we have f of x is equal to, let's say, x squared minus 10 and that g of x is just going to be equal to two x minus 3. Okay, for these two problems, okay, we're looking at the compositions f composed with g of x and g composed with f of x. And for the first item, okay, now we have f of x is equal to 2x plus 5, and we have g of x equal to 3x minus 2. Now for the first composition, okay, so we have f composed with g of x okay, and so we have f of g of x and again, so we're going to operate in accordance with f of x since we have f on the outside. So again, we have f of the input is equal to 2 times the input plus 5. Now for f of the input, with the input at g of x, you have 2 times g of x followed by the addition of 5. And for the variable expression, okay, to which g of x is defined, so 2 times g of x, you will have 2 times the quantity of 3x minus 2 followed by the addition of 5, and we have upon distributing, so 2 times g of x. Okay, that is going to become 6x minus 4. Followed by the addition of 5. Okay, and so we're going to end up at 6x plus 1. Now, in the case of the composition, whereupon we have g composed with f of x. So we're now looking at g of f of x. Okay, so output function we have along the lines of g. Input function is going to be f of x. And in terms of the delivery, that is arriving to the composition, so again we have output we have at g. Now g, the input, is equal to 3 times the input minus 2. Here, g of the input, again we have 3 times the input minus 2. And so 3 times the input, f of x. So f of x we have at 6, okay, that 2x plus 5. So 3 times the quantity of 2x plus 5, followed by the subtraction of 2. And with the distributing, okay, so we're going to have 6x plus 15 minus 2. And so we have, in this result, we have 6x plus 13. Okay, so those would be the resulting compositions for the first. Now, in the case of what we have with f of x at x squared minus 10 and g of x equal to 2x minus 3. So we have with these compositions. So f composed with g of x. Okay, so you have f of g of x. Again, it's just for what we have in the outline, so your output function is f, and by definition, f of the input is equal to the square of the input minus 10. Okay, now we have the input at g of x, so we have symbolically, we have the square of the input we have initially. Okay, well, it's going to be the square of g of x minus 10. And now for g of x, now for what that is going to be specifically, okay, we're going to have 2x minus 3, that is going to be squared, and 10 will be taken away. Now 2x minus 3 squared, again, that's going to be 2x minus 3 times itself. So you got 4x squared, and then you're going to have negative 6x and another negative 6x for the outside and inside products, and the last product from 2x minus 3 times itself is going to be 9, and then we have the minus 10 to follow. So we're going to have 4x squared minus 12x, and 9 minus 10 becomes negative 1. So we have, for the output, we have 4x squared minus 12x minus 1. And then we have in the reverse order. Okay, we have our composition, whereupon we have g composed with f of x. Okay, so we have g of f of x. And again, we have g of the input is equal to 2 times the input minus 3. And now the input we have at f of x, so you have 2 times f of x minus 3. And then for the variable expression that defines f of x, again we have x squared minus 10. Okay, so you have 2 times x squared minus 10, and then we have followed by the subtraction of 3. So we have 2x squared minus 20 upon distributing, and then we have afterwards we have the subtraction of 3, and then combining the constants. It will turn out that the composition whereupon g is composed with f of x would come out to 2x squared minus 23. All right. And in the case of operations, again, we have with the characteristics, okay, you are going to have tied in domain. And now regarding compositions, okay, in terms of their domain, okay, they're going to play by pretty much their own set of rules. And just kind of give you a kind of an intro to what we have regarding the domain of compositions. Okay, so for the domain of the composition or compositions of functions, I believe that is a singular term. So you have for the domain of the composition of functions, will be formed by combining the restrictions of the input function and of the final composition. Namely the output. And just sort of stressing again in case you have the input function and of the final composition, namely the output. Okay, and we'll say that just kind of use as kind of a building block. Now, so we'll just deal with f composed with g of x and its domain. So we have given the following. Okay, so we have, in this one case, so we have for f composed with g of x. Okay, so we have, we'll say first of all, we'll say that f of x is equal to 2x, and g of x, okay, is going to be equal to, we'll say x plus 7. Okay, so if I look at f composed with g of x, okay, so I have f composed with g of x, and for what we have in terms of following through, okay, so you have f of x is equal to x plus 7. And guess what? So we have for f of g of x, so we're going to have g of x plus 7. And just specifying what we have here. Okay, so we have, let me back up. Almost self-hypnosis. For f of x is equal to 2 times x. Okay, so for f of g of x, okay, so that's going to be 2 times g of x. Okay, and for what we have in g of x, okay, so that's going to be 2 times the quantity of x plus 7 and then we have upon distributing, okay, so we have 2x plus 14. And let me just mention, okay, so this is going to be your composition whenever we have f composed with g of x. Okay, now again we had for g of x, your input, again you have g of x is equal to x plus 7, has no restrictions, and also at the same token, the output which we have at 2x plus 14, that is the composition itself. We have, okay, there are no restrictions since we don't have anything in x that's an even root radical or denominator. And so it's going to follow that since there are no restrictions at all between the input and the output. Since there are no restrictions, it's going to follow that for the domain. Of f composed with g of x. Okay, that's going to be the set of all real numbers. And let's say that just providing just a little bit of a change up. Okay, now let's say that if we have second item, okay, and we'll say that we have f of x is equal to, let's say we had the square root of x minus 2 and we'll say that we have g of x is equal to 2x minus 14. Okay, so for what we're going to have in this composition, for f composed with g of x okay, so f of g of x, okay, so following through in line with f of x, so f the input is equal to the square root of the input minus 2. And again, so with the input of g of x, okay, so you got the square root of g of x minus 2. And once you get used to this enough, you can just go ahead and just write in the variable expression. So we're going to have the square root of 2x minus 14 followed by the subtraction of 2. And it's going to turn out that for this composition, this will wind up as the square root of 2x minus 16. Okay, all right, so that is going to be the composition here. And again, now where the domain is concerned, again, so you're looking at combining the restrictions of the input function as well as the restrictions from the final composition. Now, the input function, again, that's what is in the parentheses originally. So the input g of x, okay, and again, g of x is equal to 2x minus 14. Now that's a direct expression in x, so that part has no restrictions. Okay. Now we have with the composition, in terms of restrictions, okay, this is going to have a different story to it. Now the output, again, we have the square root of 2x minus 16. And because we have an even root radical, we have that 2x minus 16 again cannot be negative. So we have here, now it can be 0 and it can be positive. So we have 2x minus 16 is greater than or equal to 0. And if I add 16, so we have 2x is greater than or equal to 16. And with division by 2, the inequality stays in the same direction. And so looking at what we have overall between the input as well as the output. Okay, so the only restriction is going to come from the output. And this will be where x is greater than or equal to 8. So you have the number 8. Okay, for x is greater than or equal to 8. Okay, so you have a solid point on 8. And for the rest of the set, you have represented by a ray continuously going out to the right, approaching infinity. So it's going to follow that for the domain of this composition, Okay, so you have representing x is greater than or equal to 8. So we have an interval notation. Okay, so you're going to have from and including 8. So 8 is going to be bracketed. And we have going continuously out toward infinity.